I'll begin. Dear Father, we thank you for this day. I thank you for all the students are here, and some of them that are not. No, all of them. I'll thank you for all of them. And I just pray you'd be with us today, help us to glorify you in what we do, and just to learn a lot about Laplace Transforms, Lord. In your name I pray. Amen. All right, so let us begin. I guess the first question is, what are we doing? So we've solved systems of differential equations, lots of systems, right? And basically I've explained to you, if you can find eigenvectors and eigenvalues, you can unravel the matrix exponential. We can solve pretty much any system with constant coefficients, and at least up to integration that we may or may not be able to do, we can solve the inhomogeneous problem. So at this point, we turn our attention back to the nth order problem. Again, things that are, for the most part, second order. We're going to focus our attention on second or possibly first order problems. But in truth, the method I'm about to show you, it works for higher order things as well. And this is the method of Laplace transforms. Now, the method of Laplace transforms, I would say, the way I sell it to students, is that this gives us a way to treat problems with discontinuity. And of course, it also treats problems that are continuous, but if you were to have solved or tried to solve a problem with a discontinuous forcing function, like suppose, by the way, if I had asked you to solve something like y prime prime plus y equals to f of t, and that f of t had been defined, say, to be 1 for t less than say 0 for 0 less than or equal to t less than or equal to 2, t for 2 less than or equal to t, 2 less than t less than, say, pi, and then sine of t for t greater than or equal to pi. Well, this would have been unpleasant. See, because to solve this, what you had to have done is to solve it in one of these cases, right? And then you could assume that the solution was continuous because, the math shouldn't dislocate itself going from one case to the next, right? So using continuity to join the cases, then you'd solve it in the next using the previous case as a jumping off point, and then you'd find the solution in the next case and then glue it together with the previous case. You have to solve each case separately and glue them together. I often assign a homework problem like this in the first part of the course, just so you understand what a colossal pain it is to deal with discontinuous cases in our previous technology. But I liked you guys, so I didn't assign that homework problem this semester. And also, the real reason is I didn't want to talk about it in office hours, as I inevitably do if I assign the problem. I mean, that's the truth. But we will soon learn how to solve discontinuous problems using the method of Laplace transforms. That's one of the major selling points for Laplace transforms. The other selling point is that it gives us a way to solve everything we've solved before with a sort of nice, efficient algebraic technique. That's a good reason. Another good reason is that it has physical significance for electrical engineers. We're going from the time domain to something called the frequency domain. So it's part of a larger program of analysis for those folks. Now, not all of you are electrical engineers, so that doesn't matter to you as much, but it is nevertheless an important technique, which I will cover for you now. And so here it is, definition. The Laplace transform of little f of t at s is equal to the integral from 0 to infinity of e to the minus st f of t dt. All right. And this is, of course, for appropriate functions. Appropriate f of t, yeah. And so other notation, we say that the Laplace transform of the function f is equal to the function big F. So it's not an antiderivative anymore. Now it's the Laplace transform. Other notation, if we were doing, say we started with a y, then the Laplace transform would be big Y. Okay? So little y function of time, function of t, big Y function of s. All right. So this is the Laplace transformation. It's an integral transformation. Right? Obviously, it's defined in terms of an improper integral. That's pretty out there, I think. Now, there's a well-known video by an MIT professor. I forget his name, but if you search for it, if you Google it, he gives about a 40-minute, maybe 20-minute, I don't know, a long discussion about why this is natural in terms of an analogy to a discrete transformation. I'm not going to replicate that here, but if you're interested, you can look it up. I mean, there is a motivation for this in terms of an analogy to a certain discrete transformation. But ignoring that, I've never really seen anybody give a honest-to-goodness justification or motivation for why this should be the definition of the Laplace transform. I think the most convincing answer I have for you in terms of why we study this is what it does. And that's not a great answer, but it's the answer I have. Again, you can look up that article, that video by the MIT professor if you're interested. So let's get to it. What is the Laplace transform of, I don't know, let's start out small. How about 1? Right? What's the Laplace transform of 1? And so here we go. Integral from 0 to infinity of e to the minus st times 1 dt. Sorry. If I don't... oh, good. My grader's alive. Let's see here. Every so often, Kane goes dark, but he comes back after a while. He goes off the grid. But I saw him yesterday. You know, saw him. So I knew he was around. But anyway, his love of email is similar to that of Dr. Sprano. But anyway, limit as t goes to, although Dr. Sprano has gotten much better recently. Limit as t goes to infinity of the integral from 0, I mean, I'm just reminding you guys, what does the improper integral mean? This is its definition. I'm not going to belabor the definition issues for improper integration here. But here it is. This is the limit as t goes to infinity of, what's that? The integral of that is what? Minus 1 over s, right? E to the minus st, evaluate from 0 to t. Which is what? Oh, I'm sorry. I guess technically speaking, if I'm going to put a t up here, I really shouldn't put a t here as well, right? So let me fix that to be fussy. Tau. Tau. Now you won't have to tell the other math professors what a charlatan I am. There we go. Tau. I haven't misused t in duplicate ways, right? All right, great. And then, so this is the limit as t goes to infinity of minus 1 over s e to the minus st minus what? Well, plus 1 over s, right? Because e to the 0 is 1. Hey, my D-term Calculus 2 online students will soon be doing this, right? This week we cover improper integration. It's exciting. Yes. I say we cover. I'm not sure what that really means. But anyway. So what can you tell me about the limit here? This goes to 0, right? Provided what? S is greater than 0, right? So the strings attached here are that the Laplace transform of the constant 1 of s is just equal to 1 over s for s greater than 0. And there you go. Now that I've done that, you don't have to do it. I'm not doing this so that then you can reproduce my work in terms of careful and proper integration, in terms of limiting process. The point here is this is a fact that we can now use, all right? Now, I might ask you on the test to actually prove a particular Laplace transform works out to be such and so forth, but if I was to do that, I would say specifically, from the definition of Laplace transform, please show such and so forth, right? From an actuarial perspective, if you were to curate my course or something, that would be an exciting and surprising test question, because I don't think ever asked that. Because our focus is on solving differential equations, not on proving this or that basic property of the Laplace transform from the definition. But in principle, a student should be prepared for that question, right? It's within the realm of possibilities. If a student asked me the wrong question on the wrong day, and my mood was just ever so right, it could happen. All right, but it would be surprising. Okay, so anyway, moving on. What would the Laplace transform of a constant be? Well, that would be the integral from 0 to infinity of e to the minus st times a constant dt, right? But you can pull the constant out by properties of integration, right? And what's this? We just worked this out. It's 1 over s, right? So you've got c over s. So therefore, the Laplace transform of a constant is just equal to the constant divided by s, right? In fact, we can do better than this, right? Generally, I should point out that the Laplace transform of f plus g, right, is the Laplace transform of f plus the Laplace transform of g and the Laplace transform of a constant times a function, right, is the constant times the Laplace transform of the function. In other words, the Laplace transform is a linear transformation, right? Linear transformation on what, though? It's a linear transformation that goes from functions of time to functions of s, right? It's an operator because it's a function-valued function of functions. Much like we talked about smooth operators earlier, right? The derivative. But the difference with our differential operators, like the annihilator, that discussion back there, is we were taking functions of time to functions of time, right? Or functions of x to functions of x. We weren't changing the kind of functions. So this is a linear transformation, or you could say linear operator, but probably transformation is a better word because it really is a transformation. It's a transformation from functions of time to functions of s. All right? So it does enjoy linearity, though. Let's prove another theorem. Theorem. The Laplace transform of e to the, let's say, alpha t times f of t, all right, of s is equal to, and we're going to play a game, which is fill in the blank. So I was joking before class. I wasn't sure I remembered the definition. But honestly, guys, one of the things that I was so happy to learn when I first taught differential equations, because, as a student, you take a course, right? And professors say stuff. And, if they tell you, oh, you better know how to prove that, well, then you're going to work on that, right? But generally speaking, if they don't say work on how to prove that, we kind of ignore that. Most students do anyway, right? And so that was probably because I was not very mathematically mature when I took differential equations as a transfer student at NC State in 1998. I took it with Professor Fauntleroy, Dr. Fauntleroy. And he was still wearing his drawstring pants from the 70s, like His wardrobe was kind of a snapshot. I like Dr. Fuller. He's a great guy. I think he's retired now, but you know, his style of teaching differential equations, I would say, was kind of stream of consciousness. So he would just, you know, kind of put stuff on the board and just talk about it, and then I'd look back at my notes, and I don't know what I was doing. Like, it wouldn't be clear whether. So what would in retrospect, I know what happened. He would say things like, "This is a solution," right? And you write it down, and you don't know that he didn't derive the solution. He's just saying, if you plug it in, it works, right? He hasn't explained that. He hasn't shown the technique for finding that solution, right? He's just, that's a solution. And then you look back at it and you try to interpret it as being, that's an example of a technique. Well, it's not an example of a technique. It's just from the thin blue sky that he pulled the solution, right? And as a starting student, you don't know that. And you don't take very good notes because you're a transfer student and you're not used to like writing notes for a university class. It's very disconcerting. Now, I did okay, but I remember making a 50 on like a quiz in there, and high-fiving my friend Somber Paul at the time. I met Somber Paul and Crazy Paul in this class, actually. Yeah, it was a fun time. Actually, technically, I met Crazy Paul in the Liaison 24-hour computer lab at NC State, which has a very, it has the smell that you get from having a 24-hour computer lab, right, with lots of not entirely well-hygiened graduate students. So you can imagine that smell. I still smell that smell. But anyway, in that course, I was just so happy to make a 50% because everyone else was so lost. And then some other guy made 86. We're like, but we figured it out by the test. But in the meantime, it was kind of a learning curve. But one of the things I was getting to, eventually my point to this story, it will eventually get to a point, is that when I started teaching differential equations as a graduate student, at that point, I went through and derived theorems just from scratch, right, without somebody helping me. And what I realized is that the theorems in this course, they're calculus 2. Like the thing we're about to derive, it's really just calculus 2. You could discover this theorem for yourself. You don't need a math professor to prove it for you. You could figure this out for yourself. You just have to have the wherewithal to ask the question. So we're going to actually fill in the blank together here. And here it is. So take the Laplace transform of an exponential times a function. So what I was joking about was, you know what, yeah, I didn't bring my notes to class, but you know, it doesn't matter because this stuff derives itself. So here goes, e to the minus st, e to the alpha t, f of t dt. Right, that's the definition of Laplace transform. I want to see if we can't discover a better way to look at this. We're deriving right now what's called the Shift Theorem, okay? So what can we do? Well, we can combine exponentials, right? 0 to infinity, that's e to the what? Minus parentheses s minus alpha times time, yeah? Now, you might put an in-between step, you know, e to the minus st plus alpha t, but then we can factor out the minus. Now, why would I do that? Now what are we looking at? What is that? Look at the definition of Laplace transform and ask yourself the question, what have I just written down? Think about a substitution. Right? All we've done is we've written the Laplace transform of f, right? Replacing s with what? S minus alpha. But otherwise, it's the Laplace transform. So this is the Laplace transform of f of t at s minus alpha. So you might have thought that me writing of s up to this point in the lecture was just me being, you know, a pedantic math person, and it is that, that's true. But it also matters. Where we're evaluating the transform, it actually comes into play in calculations. Domain, composition of functions, it's an issue. And so there you go, that's fill in the blank. That's it. It's the Laplace transform of f of t evaluated at s minus alpha. Let me put it in terms of the other notation. in other words, the Laplace transform of e to the alpha t times f of t, all right, is equal to big F of s minus alpha. Okay? So my question for you then is, all right, great, this is the shift theorem. What is the Laplace transform of the exponential? Well, that's the Laplace transform of what? E to the alpha t times what? Times 1, right? Use your imagination. You can see it's there. But, hey, we already know what the Laplace transform of 1 is. What is it? Yeah, so this is 1 over s, right, evaluated at s minus alpha, right? In other words, it's 1 over s minus alpha. So the Laplace transform of an exponential function is just 1 over the reciprocal. It's 1 over s minus alpha. Now, if you go through the details of this, by the way, this integral converges when? There's a little bit of fine print that I've glossed over here a bit, but you know, to be clear, this is for what? For s greater than alpha. You need s greater than alpha for that integral to converge. Just like we needed s greater than 0 for this transform. All right, anyway. That actually, you know, where s is allowed to go, I don't, it doesn't seem like it's ever much of an issue in this course. But I'm sure if you continue on, that becomes something you have to think about more, so I'm not going to neglect it. Okay, great. The Laplace transform is linear. We just learned that the exponential transforms to 1 over s minus alpha. What happens when alpha is complex? What's that? You cry? No, we do not cry. We thrive. We embrace what it means for something to be complex, right? So let's suppose that we have e to the, well, let's say lambda t, and we calculate the Laplace transform of that, right? And that's going to be 1 over s minus lambda. In fact, this, you know, if lambda is equal to alpha plus I beta, the calculations that we went through actually still make sense. So suppose lambda is complex, and let's work out what this looks like then. This is 1 over, you know, s minus alpha minus I beta, right? So if you want to, you know, put it in Cartesian form, what do? We multiply by the what? Complex conjugate, right? This will put the I upstairs, and what we're going to get is s minus alpha plus I beta. And the way you want to look at the downstairs is we're multiplying this thing. Oh, man. It's off. Sad. We're multiplying this. You can live. Right? This times that. So what we get is you get this s minus alpha squared, right? The terms with I cancel out, right? Because you get plus I times s minus alpha, you get minus I times s minus alpha times beta. So those cancel. And then the I times the minus I gives me I minus I squared, which is 1. So in short, beta squared. But on the flip side of things, we have that the Laplace transform of e to the lambda t is what? Well, it's the Laplace transform of e to the alpha t cosine beta t plus I times e to the alpha t sine beta t. And because the Laplace transform is linear, I can pull the I out and I can break it up into a sum, right? This is really the Laplace transform of e to the alpha t cosine beta t of s plus I times the Laplace transform of e to the alpha t sine beta t of s. Now, let me just write the step above it just a little bit more. Just to be clear, this we can express as s minus alpha over s minus alpha squared plus beta squared, and then plus I times beta over s minus alpha squared plus beta squared. So what we have is we have calculated the Laplace transform of e to the lambda t, but we've also understood that the Laplace transform of e to the lambda t contains within it the Laplace transform as exponentials times cosine or exponentials times sine. And these two expressions I've just derived have to be equal, right? And for this complex equation to be equal, man, I feel like I'm in reruns. The real part has to equal the real part. The imaginary part has to equal the imaginary part, right? This is what, the third or fourth time in this course I've come to this point, right? This kind of point. So that has to be equal to that. And this must be equal to this. And there you go. We have derived now the Laplace transforms of the exponential times cosine and the Laplace transform of the exponential times the sine. They both give us some linear term over an irreducible quadratic in S. Sum of squares, right? You can't factor that over the reals. Interesting. All right, so we're starting to get a pretty good collection of Laplace transforms, right? We got our constants, we got our linear rule. We know how to Laplace transform a what? An exponential. We got sine, we got cosine. Hey, what if you had just a pure sine or cosine? How would that go? That's probably worth writing here. What's the Laplace transform of just cosine beta t? How'd that work out? What's the Laplace transform of just sine beta t? Those are in some sense special cases of this, right? It's worth writing those down. So in that case, alpha is 0, right? So we just get s over s squared plus beta squared, or we get beta over s squared plus beta squared. So for sine and cosine, the Laplace transforms are even simpler. Yeah. But I always like to take the opportunity to point out to you that there's deep connections between the exponential sine and cosine if we take a complex perspective. What about cosh and sinh? Let's work that out. What would be the Laplace transform of cosh beta t? What would that look like? Let's do it in pieces. So this would be 1/2 e to the beta t, right, plus e to the minus beta t by the definition of hyperbolic cosine beta t, right? Now let's use additivity. We'll pull out the half. Laplace transform of beta t plus 1/2 Laplace transform e to the minus beta t, right? What does that give us? 1 over 1/2 times 1 over what? plus, I'll put the half out here. So 1/2 of 1 over plus, 1 over something else. What's the, you got to go back to my, my exponential example. What's the Laplace transform of e to the 3t, for example? It would be 1 over s minus 3, right? So we do 1 over s minus beta for the first one. And this one, Laplace transforms to 1 over s plus beta. Hey, just for kicks, what happens if we make a common denominator here? What happens with this expression? We'd have, s plus beta plus s minus beta divided by s plus beta times s minus beta to make a common denominator. So the betas be canceling, then 2s cancels with the half, leaves us just an s over s squared minus beta squared. Isn't that beautiful? Look at that. Laplace transform a cosine, 1 over s over s squared plus beta squared. Laplace transform of hyperbolic cosine, same thing, but with a minus. In fact, if you want me to, I could color code in the formulas for Cauchy and Cinch over here. You guys ready? H, just like I planned it. That's a lie. Minus, minus. Those are the Laplace transforms of hyperbolic cosine or sine shifted by the exponential. Of course, more fun to put them over here. That just puts a minus here and here. That's actually what I tend to use. Now, do you need to use Cauchy and Cinch? Not really. But they're there if you want to think about them. I say not really because if you think about it, if you know about exponentials, right, do you really need hyperbolic cosine and sine? Well, in some sense, no, right? We can write everything in terms of exponentials of different arguments that we can write with hyperbolic sine and cosine. So why talk about hyperbolic sine and cosine? It's because they group things together which have a common identity, and they reveal patterns which are hard to see if you just use exponential notation. That's the short answer. Okay, so this is the start. Next up on the list, this is the time I give you the sheet. So this is the sheet I would encourage you to bring to the next test. Now, you don't have to, you can bring a page of notes. It can be this page of notes with extra stuff written on it. But I would encourage you that whatever you bring to the next test, make sure that you have these things on your material. I mean, you want to have these things. And it's not enough just to have these. So on occasion, I'll get a foolish differential equations class who gets the idea, oh, Dr. Cook's giving me a sheet of Laplace transforms. I don't really need to do my homework. I don't know if anybody ever really thinks this. What they think is, engineering professor such and so forth has said I need to have this project done, and that's more important than differential equations, and I'm just, you have to make choices in life, and I'll do better in the final. That's probably more the thought process, but yes.
Clarify, this is not in addition to our one page of notes. This is a supplement.
Yeah, I would, this is not in addition. You should, I would say take that and add notes to it. Or, I mean, take it to a copy machine, shrink it down to a size that you can still read. I don't know. That has a collection of everything you need to know, I think. Well, not everything. I mean, you also need to know things about trigonometry, more so for this test than previous ones. Because we'll do things like take Laplace transforms of things that require trigonometric manipulation before you can take the Laplace transform. To be more precise, for example, if I asked you to take the Laplace transform of cosine 3t times the sine of 2t, well, you'd be in trouble unless you know how to convert that to two related sine functions, right? That's like 1/2 sine of 5t minus 1/2 sine of t, or plus or minus that, something like that. I forget the plus and minus, but this can be converted into a sum of sine 5t and sum of sine of t of, with appropriate weights and signs, SIGNs. I'd have to work it out, but that's the other thing I think that is important for this test more so than others because, well, when you have the next quiz, you'll see what I'm talking about. I'll put, I'll kind of tip my hand there a little bit to what I'm talking about. But all right, so if you look on this sheet, let's look, and you notice that table 7.1, and this sheet is actually a copy of various theorems from the textbook that I've recommended you guys or required you guys to get. I forget. Anyway, Nagel, Saff, and Snyder. And so, like, what did we start with? We proved the Laplace transform of f is 1 over s, right? Then I derived 1 over s minus a, but my a was alpha. We have not done the Laplace transform of t to the n yet. We'll get to that. I've done sine, I've done cosine, and then I've done e to the e times sine and e times cosine. So I've done everything except for the t to the n, right? Although if you look at it, if you knew the Laplace transform of t to the n, you guys should understand why e to the at times t to the n is just what it is, right? You see the shift theorem at work there. See that? If you go from the third entry and relate it to the 1, 2, 3, 4, 5, 6th entry, to the third and the sixth, what's the relation? You're replacing s with s minus a. That's the shift theorem. So I'm about to, I've talked about table 7.2, the first two lines, right, additive, we can pull the constant out. The third one is the shift theorem, we derived that already. I'm about to derive the Laplace transforms of derivatives, that's up next. Then under table 7.1 and 7.2, you've got the translation in T box, that's probably a future lecture. Well, I advertise this technique as being great for doing discontinuous examples. But that's kind of my second lecture in Laplace transforms because it involves a little bit more thinking. So probably Thursday we'll do that kind of stuff, all right? And then there's a few other things. I don't usually cover Laplace transforms of periodic functions in here. There's just not quite enough time, and I'm going to leave that to your engineering course to get into that, all right? It is more subtle and difficult. Convolution we'll probably cover, but that's about it. The things I've written by hand sometimes catch students off guard. That delta is something very interesting. We'll kind of end with that. By the way, that's the Dirac delta. Okay. So let's move on here. Next up on the list is to calculate the Laplace transform of the derivative. So let's do that. A more proper math course, where we fussed about convergence and so forth, would take some time to talk about which functions can actually be Laplace transformed, right? In other words, what's the class of Laplace transformable functions? The answer is given in terms of something called exponential order alpha. I'll let you read the textbook about that. It doesn't really come into play much for us. So just a comment, there is something to think about there, but we don't really think about it, all right? All right, so up next, theorem. The Laplace transform of y prime of s is equal to fill in the blank. All right, so here we go. Proof. Again, the proof is going to be essentially calculus 2. So the Laplace transform, and let me be clear about what y prime is. That's dy dt. All right? And so what you're looking at is the integral from 0 to infinity of e to the minus st times dy dt. dt. Right. Now, what technique of integration do we use to manipulate derivatives inside integrals? You guys are not forthcoming with something. Let me remind you something. If we calculate the derivative with respect to time of e to the minus st times y, then the product rule tells me what? This is equal to minus s e to the minus st times y plus e to the minus st times dy dt. Right? But the first one by the chain rule, overall using the product rule, right? Look at what we have. What we currently have is this, right? Which is that. So I can trade that for the integral from 0 to infinity of what? d dt of e to the minus st y plus s e to the minus sty. See what I did there? I just used product rule, right? What's this technique? Of using the product rule to rewrite an integral? It has a name. It's week 1 in the D term of Calculus 132 online. Actually, they were supposed to be done by last Wednesday. In practice, most of them did it Sunday, though. Seems foolish. Whatever, though. All right, fine, I'll tell you. Integration by parts, right? Integration by parts is what we did. So I guess what I'm, well, anyway, it's not important I tell you the u and the v. That's not really the point. I've showed you a complete mathematical argument for why we can go from there to there. Now, what's the integral of the total derivative? If you'll allow me this notation, I'm going to use it. E to the minus st y. You know, that's y of t, of course, right? Evaluated from 0 to infinity. All right? Plus, and I'm going to pull the s outside the integral. Integral from e to the minus st y dt. Now, this notation, evaluation from 0 to infinity, is, of course, just a shorthand for the more proper limiting notation, right? Don't tell the other math professors I use this notation. They might not be happy with me. So it's our secret, okay? Don't worry, they wouldn't watch my videos. They're boring. Anyway, so what's that? Well, supposing that y behaves well enough, in other words, that y dies off to 0, if you think about it, in order for y to be Laplace transformable, this thing had better get small as t goes to infinity. Otherwise, the integral defining the Laplace transform of y does not exist, right? Because you're integrating this, right? For that integral to actually exist and converge, it must be going to 0 as t goes to infinity. So as we go to infinity, this must be 0. When we plug in, what happens when we plug in 0, though? Ooh, something interesting, right? So we've got e to the minus s times infinity, y of infinity. Even worse notation, guys. Don't tell the professors. E to the 0, y of 0. The point is, we can argue that this tends to 0, okay? This first piece tends to 0. That, on the other hand, what do we got here? S. What is this? I think that's the Laplace transform of y, right? So what do we got? We have s times the Laplace transform of y at s minus y of 0. And we're done. And now we can fill in the blank. So I would recommend writing it this way. This is s times big Y, all right, of s, minus little y of 0. Oh, this is kind of neat, right? Because this says the Laplace transform of a derivative somehow involves the initial condition for the function. So this is the other selling point I should emphasize, is that Laplace transforms allow elegant solutions to initial value problems. The transform itself wraps the initial conditions into the solution of the problem. We're starting to see that. Having done this once, we can do it again. What's the Laplace transform of y prime prime? Well, that should be s times the Laplace transform of y prime, right? Minus y prime of 0 by the previous theorem, right? Because the second derivative is the derivative of the first derivative. So applying the initial theorem to the first derivative, we have that immediately. And then apply our initial theorem again. So we have s times the Laplace s times s times the Laplace transform of y minus y of 0 minus y prime of 0. So what do we got? S squared Laplace transform of y of s minus s times y of 0 minus y prime of 0. Let's check our cheat sheet here. Is that what we got? We've just derived rows 4 and 5 of table 7.2 using y instead of the script f, okay? In the other notation, which I'm fond of, I would say this is s squared times big Y minus s times y of 0 minus y prime of 0. All right, if you've done it once, you've done it twice, you've done it n times, right? I mean, what's the Laplace transform of the nth derivative of y? Can you guys see the pattern? What you're going to get? You're going to get s to the n times the Laplace transform of y minus s to the n minus 1 y of 0 minus s to the n minus 2 y prime of 0 minus minus the n minus 1th derivative of 0. So you can continue this pattern. All right? One other theorem we need to derive today, and then I'm pretty much fresh out of theorems for today. Can we calculate the Laplace transform of, say, t? Let's try to work this one out. What's the Laplace transform of t times f of t? I'm a little nervous about this one. I'm not sure I remember how to do this one. You guys might have to help me out on this one. Integral from 0 to infinity. What we got? E to the minus st. T. F of t. T f of t dt, yeah. Versus the Laplace transform of f, which is what? Integral from 0 to infinity of e to the minus st f of t dt. All right, so I'm going to do something kind of wild. All right, something we don't do too much in calculus, but you can do in the appropriate context, which is to differentiate with respect to a parameter. So here, s is the parameter. And what I suggest we do is we take this and we differentiate with respect to s, holding, I'd say holding t fixed, but there's really no t to hold fixed here. T is integrated over. But let's just say differentiate with respect to s. So it's nice to use the notation big Y on this side, right? I mean, technically that's big Y of s. So what we have is we have dy ds equals to, and I'll use partial notation since there's two variables, and it seems like there's two variables involved here. Partial s of the integral from 0 to infinity of e to the minus st f of t dt. Now, it is a theorem of analysis that, given certain conditions on the function, we can commute the order of differentiation and integration. Now, I'm not going to prove it to you, but we can do that here. And so if we switch those, we have integral from 0 to infinity, right? Partial s of, well, e to the minus st f of t dt. What's this derivative? Well, I mean, what happens what's the partial derivative with respect to s of minus st? It's, yeah, we say minus what? Yeah, minus t. So this f of t has no s dependence. That pulls out of the differentiation, right? And so if you look at this, what it simplifies to is, e to the minus st times, well, minus t f of t dt. So I can pull the minus out, and we have minus integral from 0 to infinity e to the minus st t times f of t dt. So there you go. That's the relation between these two things. See what I've just shown? I have just derived for us the following theorem. The Laplace transform of t times f, right, is equal to minus the derivative with respect to s of the Laplace transform of f of t. And if you can do it once, you can do it twice, you can do it n times. What happens when we calculate the Laplace transform of like t squared? So that's minus dds of the Laplace transform of t times f, right? Which is minus dds of minus dds of the Laplace transform of f of t, right? Which we could write as minus 1 to the 2 power second derivative with respect to s of the Laplace transform of the function. I hope you see where this is going. The ultimate result here, we're leading to the Laplace transform of t to the n, right, times f of t is equal to minus 1 to the n power times the nth derivative with respect to s, dn ds to the n, of the Laplace transform of the function, which was multiplied by t. So there you go. That's our final kind of big theorem for the day. Once you know that, it's a simple matter to calculate the Laplace transforms of like t squared, t cubed, and so forth. Like, what's the Laplace transform of t? Can you guys tell me? What would the Laplace transform of t be then, as an application to this theorem? You guys tell me. So what's the Laplace transform of t? It should be what? Minus dds, the Laplace transform of 1, right? What was the Laplace transform of 1? 1 over s. What's the derivative of 1 over s? So we've got minus 1 over s squared, right? So 1 over s squared. What would the Laplace transform of t squared be? So minus DDS of the Laplace transform of t, right? Which was what? 1 over s squared, right? Which is what? Minus 1 times minus 2 over s cubed. Looks like we've got a 2 over s cubed. What's the Laplace transform of t cubed? While I'm at it. I feel like these calculations are like following me. They're chasing me across the room. So t cubed. So applying our theorem to the last result, right? So I've got minus 1 times 2 times minus 3 over, I think we start to see the pattern, right? This is 3 factorial divided by s to the 4th. So continuing, we get Laplace transform of t to the n is simply n factorial divided by s to the n plus 1. There you go. That paired with the shift theorem, we've now derived everything in table 7.1 today. All right, great. So, I mean, deriving Laplace transforms of functions is a lot of fun. I hope you got something out of what we did today, but that's, at the end of the day, not what we're actually after. We're actually after doing what? What's our goal in this course? Is to solve differential equations, right? So let me show you now how we can use this technology to solve a differential equation, all right? So, and the process of doing that, we're going to be introduced to another problem in Laplace transforms, namely the problem of, so can I mean, let me take a breath here. Everybody got the middle board, what you need down? All right, I'll give it a second. So you guys have a good weekend? Anything interesting happen? Got to meet your nephew. That sounds good. If you're a Boston Red Sox fan, I guess you're happy. Yeah. No? You're not happy that there are Boston Red Sox fans, or you're a Yankee fan? See, I'm a Yankee fan too, but I'm okay with the Boston Red Sox winning because who cares about the Dodgers? I mean, seriously. Just move to the better team. You're talking to him, right? Okay, yes. All right, I'm going to erase. So this is our first example of solving a differential equation via the technique of Laplace transforms. So here's the problem. Suppose you want to solve, I don't know, how about y prime prime plus 3y prime plus 2y equals to, I don't know, t, where I'm going to regret that, but oh well. Y of 0 equals to 0, and y prime of 0 equals to 1. So this is an initial value. This is an initial value problem, right? And you know how to solve it. You could solve this if I gave it to you, right? It's pain, but you can do it. Let's see how we solve it with Laplace transforms. So step number 1 in the technique is to take the Laplace transform of the differential equation. You see, we can do that because of table 7.2. So we take the Laplace transform of the differential equation. So we got Laplace transform of y prime prime plus 3 times the Laplace transform of y prime plus 2 times the Laplace transform of y equals to the Laplace transform of t, right? In fact, I don't even usually write this particular